talk is a bit shorter than the one at the IndabaX in the Western Cape. So, just lowering the expectations slightly. There's literally a monkey that just climbed up a ladder over there. Anyway, there's Durban for you. It's really nice to be here though, because I think there's a lot of stuff that's happening in like the Western Cape, a lot of stuff happening in Joburg. It's really cool to be here in Durban and like contributing here. So as Alex mentioned, I'm Stuart Reid. I'm currently at Aerobotics. I'm the head of data science there. What that means is that I send a lot of emails, and now and then I get to write some code, which is always fun. But what I'm going to be talking to you about today is actually like a little bit of research that I've been doing recently. When I say recently, I mean this is very new stuff. Half of it does not currently work. So I will show you some failure cases as well. But I think one of the benefits of conferences is really getting to meet people and like discuss really kind of controversial or edge ideas and where the research is going. So this is a bit of a research talk, but there is like one slide on aerobotics at the end if you guys have any specific questions on that. Also happy to take questions kind of as we go. So the talk is going to be about temporal Turing tests. So quick question, who of you have read this paper by Alan Turing called Computing, Machinery and Intelligence? So he is one of the original gangsters of like AI. Highly recommend reading this paper because it kind of introduces the concept of a Turing test. And a Turing test is this idea that that imitation is kind of the same as intelligence. So if I have a system and I can't tell whether I'm talking to a machine or whether I'm talking to another person, well then is there really much of a difference? And obviously there are very big differences, but what I'm going to be talking today is about like temporal Turing tests, so whether we can generate time series which are indistinguishable from real-world time series. And what I want to convince you of is really just one thing in this talk, which is really that deep generative models' ability to learn how to imitate without supervision, so without any labels, is going to alter our society in many more ways than we currently realize right now, because simulation is used for everything. So first I'll start off with like what is a time series. So if we're talking about temporal anything, it's really relating to time series. And a time series is really just a collection of observations ordered through time. It's not that complicated. And almost everything in the world is a time series. In fact, the world itself is a time series if you think about it. So collections of images which are taken at a particular point in time, through time, that is a time series. So I'll give you some examples of some useful time series. One of them is biomedical signals. So ECG is electrocardiogram. That's kind of like measuring electrical activity that indicates like the activity in the heart. Hopefully it's not flat, because that's when you know that you've passed on. PCG is sound waves that also are measuring heart activity. SpO2 is actually like oxygen levels. Another thing is if you're starting a startup, so if you live in Alex and my through Aerobotics world, then you might be interested in some other metrics through time, like daily active users or your customer acquisition costs or your customer lifetime values. And you might want to measure these kind of as often as possible and try to do statistical inference on that through time as you're launching new products, especially if you're following like a lean methodology. Another particularly useful time series is usage statistics. So if we're talking about network traffic, actually measuring the amount of TCP requests which are going through a network at a particular point in time, ping, latency, all of this kind of stuff is incredibly important. Earth observation data. So this is something a lot of people are like, hey, Stuart, you're into time series. Why are you working at Aerobotics now? I'm like, okay, well, we're actually taking lots and lots of images throughout the season. So it's actually like this massive time series. And what we're trying to do is help farmers grow their trees better. So we're trying to improve their yields kind of like throughout the season. So it's a very interesting problem that involves both a spatial dimension, so images, as well as this temporal dimension time series. Oh, and then let me tell you what these metrics are. NDVI is a measure of vegetation index, and you can use it on satellite data to kind of measure how particular fields are growing, that kind of stuff. NDRE is something to do with red edge, which is another layer that you should ask Scott about that. CI is like the chloroform index, which is also a measure of like plant health. And then lastly, the thing which I am probably most known for talking about is financial data. So, price earnings ratios, weekly returns, volatility index numbers, all of this is time series through time. So now that you know what a time series is, let's talk about what a simulation is. So a simulation is just an imitation of a process or a system. And simulation requires us to specify a model. Like, you cannot have a simulation without having a model, because we can't run a simulation of reality in reality. That doesn't really work. Like, we need to be able to actually have an environment in which we test. And the usefulness of a simulation is related to two things. One is goodness of fit. So how accurately does this model represent the real world that we're trying to make some sort of inference on? And the second thing is the efficiency of that model. If I can only run one pass of a simulation, I can't do a lot of statistics on that. But if I can do 10,000 iterations very quickly, that's obviously very useful. And goodness of fit is just the extent to which the model produced from the data matches reality. Okay. And then most of the time, computationally efficient simulation requires some simplifying assumptions. So the models that we're using to make inferences about the world are generally not the same as the world. Like, we have to simplify along a number of dimensions in order to run these simulations. And in many cases, like, we simplify to the point where the question becomes, well, is that simulation actually useful at all? Because if it is so simplified that it no longer represents reality, then are you just wasting your time by running these simulations at all? So I couldn't find any good pictures of simulations other than, Elon Musk kind of on Joe Rogan's podcast, smoking a blunt. But here are some images of Rick and Morty, best TV show ever, of them in a simulation. So you guys should check that out. So what matters in a simulation? I've already kind of mentioned this before, but the law of large numbers really just tells us that as we increase our sample size to infinity, our estimate that we're looking for will converge on the true estimate with 100% probability. So that's kind of under some assumptions. And the central limit theorem tells us that our error associated with that estimate as we're running the simulation will converge at the rate of square root of n. So as we increase the number of samples, we will get a better and better estimate. But what that square root of n term means is that in order to cut our error of an estimate in half, we need to increase the size of our sample 4 times. So instead of running 100 simulations, we have to run 400 simulations to cut that in half. So bias. The other thing which we rarely care about is bias. So everything I just said only holds true if we're talking about unbiased estimators. If we're talking about biased estimators, then there is no guarantee that we're going to converge on the true estimate, even if we ran an infinite number of simulations. So to kind of show what that looks like is like, here's some metric that we're trying to compute, and as we run more and more and more samples, our distribution of the possible values that estimate could be kind of converges, and it converges at a rate of square root of n. So where is simulation used? So we can use simulation for anomaly detection. So if you run a very large number of simulations and you know what the outcomes should be at any point in time, you can kind of like compute the probabilities and say, well, this has happened almost never, so therefore that's an anomaly. You guys can ask questions as we go, by the way. Okay. Now this is what I did in my previous life. I've had a few lives now, but I spent a lot of time doing options pricing and risk management. So to tell you guys what that is, like financial markets, we have these things called derivatives, and the value of this security is derived from the value of some other security kind of through time. And generally, what we want to be able to do is say, well, what is this derivative worth, given the statistical properties of the asset on which it is based, right? So how we mostly do that in finance is we will fit a stochastic process to some security. So like, let's say you want to work out what an option on Nussbaris is, right? We'll fit a stochastic process to what happens to Nussbaris generally, generate many thousands of examples and say, well, listen, this option is only in the money like 1% of the time, so therefore I'm not going to charge you a lot to sell you this option because there's a 99% chance that it's not going to be worth anything in 3 months or 6 months or a year's time. So really, it just comes down to probabilities. So you can kind of see that here where we have different paths that could be generated in a particular process, and we draw a distribution over where those paths end up, and from that we can really derive the value of a particular security. Okay, but don't forget, and this is the important thing, the usefulness of any simulation is directly proportional. I changed the quote slightly to make it a bit longer so it fits in the lines nicely. Directly proportional to the goodness of fit and efficiency of the model. Okay. So what do time series have? This is my favorite slide. They have different frequencies. So some data might come out quarterly, some daily, some hourly. They have trends. You could have linear trends in your data. You could have exponential trends. You could have logarithmic trends. They have persistence and memory, especially some processes have very, very long-term memory that is particularly hard to model with machine learning models. They could have seasonality components, so they could be a yearly frequency, a monthly frequency, some sort of weekly frequency. Like if we're talking about demand forecasting for electricity grids, for example, there is a difference if you're in summer or winter. That's a seasonal kind of component. There are autocorrelations, so there's a relationship between the value of a time series right now and the value over some previous number of time steps. It's not a completely Markovian process where we just generate kind of values as we go and none of the previous values matter at all. There are also cross correlations, so most of the time we're not talking about one time series by itself, which is the majority of models that we have for dealing with the previous issues, right? Most of the time we're talking about a system of time series, and what we're interested in how the system kind of evolves through time. So we could have a portfolio of assets, or maybe we're not talking about one power station, we're talking about 17 power stations, and we're interested in modeling the relationships between those things. So those are cross correlations. There are non-stationary dynamics, so you could have very, very complex non-stationary features which cannot be captured by linear models or linear trends. There's also conditional heteroscedasticity, which is the idea that you might have increasing variance over time, which means that if you fit a model, you could actually find the model getting continuously worse and worse as you go forward in time. There's also a lot of randomness in time series. A lot of measurements are just noise, and I think 90% of financial data is just randomness, which is why random walk models are actually surprisingly unreasonably effective, right? And then lastly, something that's been touched on in a few talks is causal relationships. So there could be very strong causal relationships between different time series, or between some very infrequent event and the outcomes in a time series, load shedding is tied to power stations kind of not running, right? So what I always like to say about time series in machine learning is that they're the red-headed stepchild of machine learning. Nobody wants to touch these things, so I was looking for a nice picture, and that's kind of what I came up with, right? That's what time series are in my head. It's pretty scary. I have nightmares every night about it. So what do our models have? This is a good question, right? So this is what the real world has. Like the previous slide, it's the real world is complicated, it's messy, there's a lot of dimensions to it. So what are the models that I used to use for pricing derivatives have in them? So if we're talking about options pricing with stochastic processes, we'll generally just assume that some random walk represents these time series, and we assume that that distribution from which we sample is stationary through time. We assume that there's no memory at all. Not only is there no short-term memory, so there's no relationship between successive points in the time series, but there's no relationship between the point now and the point 3 months ago or the point a year ago. We assume that there are no deterministic components, everything is entirely governed by probability distributions and randomness. And there is no causality at all. It's just randomness. The point of the slide is just to say that literally we assume that there is nothing when there is in fact a lot of things. So, There are some models out there that will relax these assumptions. There's like the Heston stochastic volatility model, there's the Merton model, there's the Hull-White model, and these will introduce like certain components, they'll add them back. But most of the time what you end up with is something that looks nothing like reality. So this is an example of some real financial time series data. You can see a few different features. You can see that the volatility is kind of clustered at specific points. There's outliers, and they tend to be quite close together, right? And this is what gets produced by like parametric models generally. So as you can see, there's no relationship between these two things. They look rather different, which then begs the question, well, if I had to run a simulation and I had to have like 200 servers and I ran 10,000 or 100,000 options pricings with this model, would it tell me anything about the world in which I live? Probably not, which is kind of what I'm getting to. So does any of this actually matter? Maybe not. I mean, let's make the case that it doesn't matter. If humans can't tell the difference between stochastic processes and financial time series, are they good enough, right? So this is a picture that I used to have in our presentations. And one of them is real and one of them is random. So raise your hand if you think the real one is a real financial time series, the red one, if you think it's real. No one's raising their hand. Do you all think the black one is a real financial time series? That is impossible. They're both random. All right, so the truth behind the slide is that I generated it like 2.5 years ago, and I can't remember which one is which. Okay, like objective truth. So maybe it doesn't matter. Like, if we can't tell the difference, maybe it doesn't matter at all, okay? Or maybe it does matter, The incorrect applications of really shitty models, like the one I just showed you, have caused a rather large amount of damage to our society. And there are a lot of books written about this. The first one is When Genius Failed, about when long-term capital management, a very famous hedge fund, created and left a $1 trillion hole in the US equities or bond market. And then this one, The Big Short, great movie as well, is really about the financial crisis. And they don't touch on it too much, but the models we were using to price collateralized debt obligations and credit default swaps were like assuming a normal distribution on the correlations. And it's like, basically it's like saying, if your neighbor and your neighbor's neighbor foreclose on their house, it has no relationship at all to whether your house has any value. So like the assumptions that we had in these models were ridiculous. There's also some great talks or some great books about randomness in financial markets over here. So this is a conference on deep learning. I have not said anything about deep learning yet, but I'm getting there, okay. So deep generative models' ability to learn how to imitate without supervision will radically alter our society. This is what I want to convince you of. And the idea that I'm going to present is that we can actually use deep learning models to replace 100 years worth of stochastic process theory that has been developed in financial markets and in other fields, and we'll get better results. So this is kind of what I'm working towards. So we're just going to throw 100 years of research away because it's crap. Deep generative models. The first model which I'm going to talk to you about now is a variational autoencoder. So a variational autoencoder is, it was mentioned in the talk this morning, an autoassociative. That was the old name for it. But basically how this model works is we pass our data from the input through to the output, and we pass it through two layers in the middle that actually correspond to the means and the variances of a multivariate normal distribution. And what we do is we say we want this normal distribution in the middle to remain normal as we're training, so as we're reproducing the input data that we're feeding in. And how we do that is we add an additional loss to our neural network, which basically penalizes it for becoming non-normal. And how this trick works is actually the reparameterization trick, which is this idea that we can backprop through standard deviations on these normal distributions. But the point is that we feed in data, we reconstruct it like a normal autoencoder, but we pass it through a probability distribution, which allows us to do one thing. We can throw away the encoder part. We can just sample from our prior, which is a normal distribution, and we can decode processes that look exactly the same as what we'd learned the processes look like. Deep or generative adversarial networks. So GANs work by basically breaking the problem of like sampling time series into two components. So you'll have a discriminator and a generator, and they kind of like play each other to become better. And they essentially learn a loss function for generating realistic data. So this is the progression of GANs for generating faces through time. You can see that it's generally getting better. And what's interesting about GANs is that we're actually trying to learn the loss function. The generator's objective is to make the discriminator as bad as possible. So I'm getting to the end now. But I've trained some variational autoencoders to generate some biomedical signals because it's very hard to tell if your model is not working. And I have two images. So the top half and the bottom half, one of them is real and one of them is fake. So let's try this again. You guys failed earlier. Everybody who thinks the top is real, raise your hands. All right, roughly 50% of the room, score. Like that is what I was going for. So the top is real and the bottom is fake. But as you can tell, they're rather similar, which means we're actually learning how to generate, synthesize from scratch biomedical signals. On financial data, we are currently able to learn stochastic volatility, clustered outliers, cross-correlations, autocorrelation, and regime switching. And what I showed you earlier was that graph where it didn't look anything like reality. This is actually what gets generated from variational autoencoders. So we're getting many of the characteristics that we get in real data from our synthetic data. Cool, so some headaches along this process. One of them has been mode collapse. So sometimes the model learns to just predict one value and it kind of gives up. So with some custom loss functions, I've been able to get the variational autoencoders to generate data, which is very similar to the real data. And this is open source, I'll tweet out a link. But as you can see, it's still kind of underfitting on the distribution. Another headache has been recursive sampling. So unlike an image where we encode and then we decode and we know exactly the dimensions of the image, a time series could be 60,000 data points or 2 million data points long. So I'm actually using a recursive sampling scheme where I generate 20 points at a time, and I could end up generating 16,000 data points to actually show that electrocardiogram graph, right? Which means that you're recursively conditioning yourself on your previous values. Like you're generating recursively, which if you're using certain types of models, especially convolutional neural networks, you can recursively generate yourself into a very, very weird place. So there's some graphs which just kind of like go up and to the right. Very unhealthy patients. Other issues, TensorFlow 2, everything is implemented in TensorFlow 2 because there are some really nice features. The TensorFlow probability layers now come out as distributions, which means you can actually sample from layers, which is pretty dope. But they have this little proviso which says, you will likely find some bugs. Yeah, I found a lot of freaking bugs. I'll show you one. So look at the run times. It goes from 25 seconds to pass through 63,000 data points up to 123 seconds, and it just keeps on growing exponentially. So I kind of constrained myself to train the model within 25 epochs. So the results, everything I've shown you is like only in 25 epochs because I run out of RAM and my computer breaks after that. Okay, so conclusions, like the so what of the whole talk. Basically, I think if we can generate data which is more realistic than most of the stochastic process and parametric models that we've been using, whether it be in healthcare, engineering, finance, different domains, we can actually make far more reliable estimations about the world that we live in. Next steps, currently working on recurrent and conditional GANs. I tweeted this out recently, built my first GAN, producing total garbage. That's the results at the moment. The GAN has learned that if it generates a lot of noise, the discriminator struggles. So I'm still working on that. And then sneaky product placement. I work at Aerobotics. We are currently hiring data scientists. I'm currently managing the yield team, where we are trying to estimate fruit sizes and the percentage of fruit that will be of export quality and a number of different metrics by flying drones really low above farms and using computer vision models. And then we've also started this really cool computer vision meetup working group where anybody who is doing computer vision research in Cape Town is invited to attend. So if you're interested, please come join us. And that's it. Thank you for having me.
That was a super cool talk. I wanted to understand a little bit more about when you're like synthesizing or generating data, how do you actually synthesize seasonality?
Yeah, so like synthesizing like seasonality, the cool thing about these models is that they learn all of the features that they need to learn in order to reproduce, so reconstruction loss if we're talking about the variational autoencoders, or if we're talking about, again, to actually trick the discriminator. So hopefully it encodes the seasonality or the time of year into that latent representation that it learns. And then when it recursively samples, it sees more and more and more of what it has sampled, and then it uses kind of the history of what it's generated to know what season it's in. So I haven't tried with any like very clearly seasonal time series yet, but the graphs I showed on the biomedical, like those heartbeats occur over about a 2,000 time step kind of period, and I'm only generating 20 points at a time. So it does actually know that like it should generate this now, even though like there's a very long-term dependence there.
When you talk about randomness of time series data and why researchers run away from time series data, I deeply understand what you're talking about, because I work with time series data, and sometimes I train my model, I test data that was gotten from the internet and it works well. I got the real life data and I put it in there and nothing works. Yeah. All right. So I have one question. We're talking about GAN. How do you write the fitness function, or how do you describe the fitness of those discriminative model and generative model? How you talked about them, trying to, fight with each other, if I use that term. So, the fitness, how do you go about evaluating their performance? So, what fitness measure do you use? It's easy to say, well, discriminative model try to work against generative, and generative work against discriminative. That is not talking about. Can you please get a little bit deep how you evaluate fitness? Thank you.
Yeah. Cool. So like I mentioned, I'm quite new to GANs and I'm still struggling with them. But I mean, essentially how it works is you have the generator generate some real samples and some fake samples, and then you have real samples that are drawn from like your data, which you have available to you. And then what you do is you see if you can get the discriminator to get a very high accuracy in working out which ones are real and fake. And then what you do is you kind of use the discriminator's outputs as the loss function for the generator. So I can show you like how those things plug together, like the code is like open source, and I can show you like the details. But essentially the discriminator is the loss function for the generator, which is a very powerful concept, because now we don't have to go and design our own custom loss functions which capture all of the very complex stylized facts about financial time series or time series in general. We can actually learn those from the discriminator. But the challenge there is kind of getting the discriminator and the generator to play well together. That's been the challenge that I've been having. But yeah, I mean, let's take it offline, and I want to hear about what time series you work out. It sounds like you've been struggling.
One more very quick one, sort of yes/no answer. Do you think that we are currently sampling again through time, or some of the people?
Yeah, I think this is a simulation as well. Yeah, 100%.
There you have it. Okay. Thanks again to Stuart.
We'll chat just now.